他一会儿就开始。你坐哪儿？坐我后面。哎呀，对，我也要作业噼里啪。啊，对，开始了，平常就没有到5，我就做开始。上次我
This is just basically learning how to calm down.
没有到5。刚才我在外面的时候，我是在上学，我还提前10分钟就回过去，然后是。
So is it just because I didn't label it?
So you should.
It's got a 1 and then that would be.
We've also heard it, so it's supposed to come up.
Wait. Your FOP is the same. Because I asked you for FOP.
没有，我今天还有聊是等会儿看快点。Slack。
Lower than.
I thought I ended up.
Lower than the yeah.
是吧？有人。
Right.
I thought that I had.
So it's right.
There's another half.
I think you got it right.
Yes, thank you.
I'm gonna ask. I'm just gonna ask. For this solution, is that's not the right representation of the solution?
What is this? What is this?
Oh, that was me trying to reduce it down to 1 by 1 by so 1/2 minus.
Yeah, but how can you have the shape?
But it's mostly the small.
So that's why I ended up having this. Okay, so that's an intercept of 1.
No,
没准不行，好像不行。但是今天非常奇怪的是，我开的这个软件好像之前有人用过这个相机的，就是它那个有2个摄像头，不知道为什么，好像上一期。
So you have intersects at 1, 1.5. Then you write down the intersect.
不知道它是怎么回事。
I forgot the invert. That's what it is.
She's not giving you any points.
Yeah, I should have told you. No, totally. Cool. That's what I wanted to figure out.
Just get circles out.
Cool.
It's pretty interesting, honestly, though.
So that's definitely
Used to do it.
Oh, sure. Can you like? Some of them actually had, like, for
It's
example,
just super cool.
not it was not this batch.
It's
That's fine.
you work for recreation and
It's like real.
hopefully.
But he said it's too
But then after that, or no, after
yeah. Yeah, right. Always each cross.
yeah.
He was like, his wife got 5 points here. No, I can do this. Just let me know. I can get a feel for most of them. Is that okay? And then once I did this, upload the code and post it on. So did they ask you a lot of questions yesterday? Okay, they asked you a lot of questions. So the good thing is next homework or we can go those solutions so we can get them. All those very solved. Getting emails explaining it. But the quiz is like fantastic. I was like
Because you're doing a lot. But it's just funny because it's making a child kill someone. Like, you know, like things like that, where you're talking about insurance, so it's like, yeah, that's
Children, long time no see. That's one day I was one day I was
我觉得我只知道你说了一个人。
and then you just and that was like, I actually I think that's exactly like that. Yes.
Okay, everyone. Then we should start. So just a reminder again, next Monday we'll have a quiz, the first quiz. So be sure to show up in our first quiz, otherwise you will have a 0 score. Quiz does it is taking into account the final score if you can review the syllabus. And quiz plus homework takes 80% of the final grade, and final exam takes 20%. So although we have a policy that among all the scores for the quizzes and homeworks will automatically drop the lowest score, but at least you can try. You can try for all 5 and pick then throw out the lowest one. Right? If you just miss it, then automatically that comes just 0. Okay. So let's continue the class. So in the last lecture, we discussed a set of IID data points. Right? So basically, we have n data points, x1 to xn. So we usually assume they are IID. What does IID mean? This is a very commonly used assumption. So x1 and xn are usually represented as like n data points in your data set, right? And to analyze this data, a very commonly used assumption is that we assume these n data points are IID. So what does IID mean? Yeah, I heard someone has explained it. So IID means independent, identically distributed, right? Independent means that this n data points or random variables are independent to each other, meaning that their value they take have nothing to do with others. This is called independent. And then what does it mean for being identically distributed?
They have the same PDF?
Yeah, just as the name suggested. So meaning that, okay, we know that x1 follows a hidden distribution f, and x2 follows exactly the same distribution f, until xn. This is what IID means. And given the concept of IID, we introduced the average of those data points, which we call it sample mean, because it is just the average of these values of n random variables. This is called sample mean. So we use sample mean to estimate the true mean for this underlying distribution f. We discussed why it is reasonable to use the average, namely sample mean, to estimate the true mean. Why? An idea? So first we examine, remember, this sample mean is a random variable as well, because this is just average of n random variables. Right? You do the operation over a set of random variables, you end up with another random variable. So sample mean must be a random variable. And then to examine whether this approximation is reasonable, the first step we check is to say whether the expectation of this random variable, meaning the expectation of sample mean, it is equal to the true mean, right? We first check this point. And indeed it is. You can use the expectation operation we have reviewed to calculate. It's very straightforward. So at least we know that when you use sample mean to estimate the true mean, there is no systematic error. On average, we know it must be the true mean. And then what kind of properties about the sample mean did we check? I will also talk about another naive estimation method, right? That is, among those n data points, we just randomly pick up one data point, say x2. We use why not we use x2 to estimate the true mean? Because the expectation of x2 is exactly the true mean as well, right? According to our IID assumption. Then why not we use x2 directly? Why should we use this one? We use a sample mean, we take the average. What's the benefit of using this rather than randomly pick up a data point?
The variance is lower.
Yeah, exactly, right? We compare the variance of the sample mean with the variance of any data points, say x2, right? So what's the variance of the sample mean? It is a variance, you can verify it off class, but it's, let me just write down the conclusion. It is a variance divided by the number of samples. So now we can see the variance of the sample mean is related to the number of data points in our data set. Right? So the larger the number of data points, the smaller the variance, meaning that the larger the chance that this sample mean is close to the true mean. And as a comparison, the variance for x2 is the variance for the hidden distribution f directly, right? So it has a much larger variance than the variance of sample mean. And to explain why smaller variance is better. And then we discuss the distribution of sample mean. What's the property of the distribution of sample mean? Yeah. A famous theory characterized the distribution of sample mean is called the central limit theory. It just states that whatever underlying distribution you have, the sample mean, namely the average of the set of ID random variables from this distribution, actually looks more and more like a normal distribution. And the mean of the normal distribution would be the mean of the true underlying distribution. And the variance would be the variance over n. So meaning that when you increase n, increase the number of data points in your data set, then the distribution of this sample mean becomes closer and closer to a Gaussian distribution or normal distribution. But this Gaussian distribution, which this sample mean distribution resembles, has a smaller and smaller variance because this is variance. Right? So this Gaussian becomes thinner and thinner. If the PDF curve now comes into your mind, it's a bell, right? The bell becomes thinner and thinner. So this is about central limit theory. The sample mean and the true mean. This, for example, can we state that, or can we assert that this error is always less than 0.01? Can we state that?
With more, maybe, if we can? With more n?
No, it's not more. Just think about it. Because this is just a way I calculate sample mean as an estimation of the true mean. Right? This true mean is something we're really interested in. And then to quantify or to measure the performance of this kind of estimation, I want to get some guarantee. I want to get some assertion about that, right? And naturally, I would like to ask myself whether I can bound the error, whether I can state that this error is always less than like 0.01. If I can state that, maybe from my perspective, or from my application, it is enough. But the question would be, can we make such kind of statement? An idea? The answer is no. Why? Because this is not a deterministic value. This is a random variable. So when you collect the data set, which consists of n ID data points the first time, you get values for x1, x2, and values for xn. Right? And then you calculate the sample mean by averaging these values. You end up with one sample for the sample mean. Now you can calculate the error if you know the true mean. Right? Say this time it could be 0.5, and it is less than this value. I'm happy with that. But you cannot guarantee next time you still obtain the same error. Right? Next time we'll collect another data set. Then the values for each data point could change. And accordingly, the value for the sample mean changes as well. So as the error. So next time could be like 0.5. So then there naturally comes a question. How can we use some mathematical language assert the range of the error? Or to assert the range of error, what kind of extra steps we need to incorporate? An idea? First, this error, namely the difference between the sample mean and the true mean, It's not deterministic, right? It is a random variable. Everyone agrees with that, right? And now how can we describe the behavior of a random variable? Yeah, exactly, right? That's the tool we are discussing so far, right? The most appropriate way or most rigorous framework to quantify the randomness of behavior of random variables is probability. So we can, in this case, to characterize the range of the error, a simple such kind of bound is not enough, right? Because it is random. So we need also to know the probability of this error is less than or equal to some specific level, right? So I'm interested in whether the probability of this error less than 0.01 is big enough. Because this is a random variable, we cannot guarantee it must happen, right? There could always be some chance the random error is bigger than 0.01. But if we can say, okay, the probability of error less than 0.01 is relatively large, say 0.099, maybe it's good enough, right? Namely that when I collect the data set 100 times, and 99 times when I use the data set to calculate the sample mean as estimation, the error will be less than 0.01. Right? Only one chance I got failure. That's okay. Right? That's fine. And nothing better than this. So now we can say, in this simple true mean estimation problem, to quantify the range of the error, we not only need some deterministic value, we also need to quantify the corresponding probability. Then another question would be, can we calculate this probability? Can we do that? Or any idea that comes into your mind, you think could be useful to compute this probability? So if we can do that, then we're happy, right? So although we can now say, given some specific error level, say less than epsilon, the error must be less than epsilon. But I can know what's the probability it is less than epsilon, right? That's pretty enough. But unfortunately, in most cases, we cannot quantify this probability. Although according to central limit theory, we know that the distribution of the sample mean resembles more and more normal distribution. Right? But central limit theory never assure you the distribution of a sample mean. It is a Gaussian or normal distribution, meaning that it's actually not reliable to use a Gaussian to approximate sample means distribution. Then how about, then what can we do with that? So in general, how can we know the probability that our error is less than some specific level? How can we do that? So here comes the idea called probably approximately correct framework. So probably approximately correct framework called PAC framework, which is a very fundamental framework in computational learning theory. Although I don't know how you feel that. Every time I raise it, I feel quite difficult to pronounce it. Maybe this is because I'm not a native speaker. But actually the idea behind this PAC learning framework is very easy. It's actually a compromise between the reality and theory. So we're not able to compute this probability that the error is less than some specific level. And now we step back. We make some compromise. We want to find out a bound for this probability. If we can find a bound for this probability, at least we are certain about this chance in some level, right? So let me write it in another way, a totally equivalent way, and then we discuss this bound. So this is equivalent to say the probability of the error bigger than some specific level, less than delta. Any question about this? These two inequalities are totally equivalent. Any question about this?
What is delta represent?
Delta is some bound, some value we want to look for. So as I just said, the promising thing is that we can directly compute this probability, right? But in reality, this is usually infeasible. Then what's the compromise do we make to quantify or to measure the performance of our estimation? We instead of computing this probability accurately, we just found a bound for this probability. So the packed learning framework aims to find such a delta to construct such a bound. So for convenience, you can just subtract this inequality by 1 right, on both sides. That means you just reverse the bigger to be less, right? And then you end up with this. Yeah, you can say greater equal to or whatever, like this. It's fine.
Shouldn't the inverse of the first one is, if the first line is smaller than the second one is greater than equal? One of them should be has equal sign, and another one don't have equal sign.
Oh, that's fine. That's just a tiny detail. Don't worry about that. So yeah, you can see it like this. Yeah. More rigorously, it will be like this. Or I can assume I just want to quantify this bound, and when I do the subtraction, I end up with this. Anyone is confusing about this transformation? I think it's pretty straightforward. Right? And now we can look at this probability again. So what does this probability mean? It means the chance that the error, namely the difference between your sample mean and the true mean, is bigger than some level. Right? And our objective is to find out a upper bound for this chance. This is actually the main task for the computational learning theory. And later I will explain why this is the main task. So our objective is to, given some specific epsilon, say 0.001, to find out a bound for this probability to be as small as possible. So the smaller the upper bound, the tighter the upper bound, the better you can quantify this probability, right? So for example, if I can state that the error bigger than 0.001 is less than or equal to 0.001. What does it mean? It means that the chance that our sample mean deviates the true mean by 0.001 is very, very low, right? Just less than 0.001. Then I'm pretty happy with that. But if we can only say the chance that the probability, the chance that the sample mean deviates from true mean from 0.001 is only less than 0.5, then I'm not satisfied with that. Why? Because I'm not sure how rare the case that the sample mean is far away from the true mean. Right? Any question about this?
If we can do some examples to see how this works in action.
Works well.
Can we do some examples?
Yeah. So if I use any other estimators, say X, from the set of IID samples, whatever, you can do the average that ends up with a sample mean, or you can do any other method. Right? Then I want to evaluate the performance of using your own method to estimate the true mean. Then what can you do? Right? So the method we are using right now to evaluate performance is to find a upper bound of the probability this error bigger than 0.01 is less than something. I want to find an upper bound for this probability. So suppose I found the upper bound to be 0.002. What can I claim from this? Think about it. What can I claim?
Does that mean our threshold for saying that we're comparing a certain error range that means we're probably approximately correct?
Later I will explain why it is associated with these three terms. But from this inequality, what can we claim is that we use this X circle to estimate the sample mean. I can assert that no matter how you collect the data, no matter how you do this, how many times do you do this, I know the probability your estimation error bigger than 0.01 is relatively small, right? And the chance is very low, like 0.002, meaning that in the 99.8% chance, the error is less than 0.01. As a comparison, suppose Mr. Smart invents another method, like let me denote that as a X triangle to estimate true mean. And now, I derive the bound for this X triangle, the error for this X triangle to estimate true mean bigger than 0.01 is less than or equal to 0.2. That's the bound I derived for another estimation method. Right? And now compare X circle and X triangle. Which one do you think is better?
The first one. The circle.
Yeah, why is first one?
Because it has a lower upper bound.
Yeah, because from first one I can say, okay, the chance that this error beyond 0.01 is very, very low, right? But for the same event, namely the chance for X triangle beyond the true mean by 0.01 is relatively large. So now you can see how this probability inequality shows the performance of your estimation method. So this is kind of not very straightforward, because you need some time to consume it and concern and think of why it is reasonable. But it is reasonable. It's actually the best trade-off between the reality and the theoretical guarantees you can get. The reason is that we can never compute the exact probability, so we can only find some bound. And now let us look at this bound again. So our task is to find a bound delta for any given epsilon. So this procedure or this process is generally referred to as a probably approximate correct. Why is probably?
There's no guarantee.
Yeah, there's no guarantee. We have to incorporate some probability. It's actually the bound for the probability. And why it is approximate? Why it is approximate correct?
Because there's still room for error.
Yeah, there is an error level here, epsilon. Right? That's why it's called probably approximate correct. So usually we refer this epsilon here as tolerance level. Meaning that in what kind of error level we want to investigate. Right? What kind of tolerance level we want to investigate about the error. And this upper bound we aim to find is usually referred to as a probability failure. Of failure. So usually we treat this event, namely our sample mean beyond the true mean by epsilon as kind of failure events. Why? Because we do not want their difference to be large. And then we bound this probability. We found bound for this probability. That's why we call this bound as probability of failure. So in general, in computational learning theory, we use the so-called probably approximate correct framework to bound the generalization performance of your learning algorithm. So now let me illustrate how it connects to this probability bound. So as we discussed in previous lectures, we know that the core task of data mining or machine learning is to aim for a model from some data, right? But here we know that data is random, meaning that this time I got a set of data, next time I got another set of data. They could be different. Right? That means this time when I estimate one model, next time when I estimate another model using exactly the same algorithm, but the two models could be different. So meaning that the model is essentially a random variable. This is something you should be aware of. There's no certainty in data science or machine learning. There is always some uncertainty because the data, the sources where doing things is random. And then suppose we have already trained on the data to get some model. How can we evaluate the performance of model? I'll commonly use methods to make prediction. Say I want to predict whether this image contains some products, or want to predict whether this recommended book, I like it or not. I use a set of task data. So let me denote it as X star. And also I know the true label of this test data set. And then what should I do to test the learned model M on some particular data set? I use some prediction function, right? So I predict the test data X star using the learned model from the training data D. And then to evaluate the performance, I just compute the error, right? The difference between the ground truth label and the prediction by our model. This is a metric we used to measure the performance of our model. Your question?
Sorry, what does Y star stand for? Is that the model, the algorithm?
Y star is some answer. For example, I want to test whether your model is good at predicting this image contains cat or not. Right? So I train such a model, and then what should I test? I collect a set of images. Some of them contain cats, some of them contain dogs. And then I use my learned model to predict whether each of the test image contains cat or dog. Right? And then I compare the difference between the answers and the prediction by my model.
So X star is the labeled data set,
Yes, X star like the images.
and then Y star is what you get when you put X star through the model.
Yes, but Y star is a true answer.
Yeah.
And your prediction of your model could be another Y, right? This Y could be different from Y star. Yeah. There is some error. So naturally there comes a question. So if sometime for a particular data set, I got error through this measure to be like 0.001, can we claim that our model performs very, very good? No, actually. Why? Because this is trained on one specific data set, right? On one specific data set, okay, I got one model and we get a small error. But can you guarantee next time when you get another data set and train the model again, you get a similar error or same error?
Is that the example of overfitting?
No, it's not overfitting.
No, it's not.
Nothing to do with it. We're not talking about overfitting. Probably we'll mention a little bit, but we're not going deeply over that concept. So we're just talking about how to measure the performance of your learning algorithm. In one-time training procedure, the model learned by learning algorithm has a very good performance. Does not mean it will always have very good performance, right? It depends on the training data as well. Then how can we derive some theoretical guarantee about the performance of your model or your learning algorithm?
We can find the probability like you did.
Yeah, here are how we connect here. Because this error is a random variable as well. So you want to characterize the probability of this error bigger than some specific level. What's the upper bound for this? When we get such kind of estimation, we have kind of knowledge about the performance of this model. That's how this PAC framework relates to the evaluation metric of the machine learning algorithms. But this is mainly for a theoretical perspective, because in theoretical perspective, we want to some conclusion which is for sure, right? Not some empirical. For empirical, okay, I can do this experiment like 10 times, right? Each time I got a different data set, and I test on same task data set, I got 10 errors, right? And then I have a relatively estimation about the possible error in average. But from theory, if we want to get a trustable, a justifiable theory, we must state something which holds for whatever kind of situations. That's why we should use this. And it turns out this is one core task in computational learning theory or machine learning theory. For any particular type of model, particular type of algorithm, I want to find a bound for this prediction error bigger than epsilon, less than delta. Our objective is to find this bound. And this procedure could be very, very complicated. But it turns out that deriving the bound for this probability, most of the time, is attributed to bound the probability for some random variable. Deviates from its expectation bigger than epsilon. So remember these two things is different from x minus ex. This is random variable, for sure. But there is no guarantee that the expectation of this random variable will be the true label y star. So this is not directly applied here. But in the process, in many proofs of computational learning theory, to derive the upper bound for this probability, you do some many derivations, right? Your proof steps, and finally, it ends up with bound the probability for some random variable. Deviates from the expectation bigger than epsilon. So if you register my next semester's class, you will see a few examples of doing this. But in this fall, in this class, we won't introduce a detailed example of this. We only need to know some commonly used simple tricks to bound the probability for a random variable deviating from its expectation by epsilon. That's the main topic we're discussing today. It's called concentration inequality. Why is this called concentration? As the name suggests, Ex is a concentration of the expectation of X, concentration of a random variable X. And we will introduce three commonly used and basic probability or concentration inequalities to obtain a bound for this probability, namely Markov inequality, Chebyshev inequality, and Chernoff-Hopkins inequality. And the three inequalities are becoming more and more powerful in that the bound you obtain by using the three inequalities is tighter and tighter. But there's no free lunch. If you want to get a tighter bound, meaning that you get more accurate bound, right? You need to know more information about this random variable X. We'll now introduce the proof of the three concentration inequalities. You're required to know how to apply the three inequalities to derive the bound. So let us look at the three inequalities one by one. So first one is called Markov inequality. Forgive my writing. Let's mix up. So what does Markov inequality says? It says that for a non-negative random variable, so here X must be non-negative. It says that the probability of X is bigger than some positive value alpha. It's bigger than or equal to, less than or equal to expectation of X or alpha. This is Markov inequality. Very simple. All you need to know is the expectation of X. But you also need to know the restriction for X. It must be non-negative. Why it must be non-negative? You can imagine if X is negative, what will happen? So if X is could be negative, then expectation X could be negative. Okay? And now this upper bound becomes negative. And can you imagine a probability is less than a negative number? It's not possible. Probability must be non-negative. So whenever you're using Markov inequality, keep in mind that the random variable must be non-negative. So now let us look at two examples and see how this bound is affected by the properties of X, namely how X is distributed. So suppose right now I set alpha equals to 5. So I want to bound probability that X is bigger than 5 using Markov inequality. So suppose in the first case, the PDF for the X is like this. The probability density function is like this. And here is 5. And here say to be 3. So what's the probability of X is bigger than or equal to 5? It's actually the shaded region here, the area of here. Why? Because this probability is strictly the integral of the probability density function from 5 to infinity. Right? This is the definition. an integral over a function is actually error. The error the PDF curve covers from 5 to infinity. And now we bound this probability, namely that we bound this error. And now suppose, according to this PDF curve, we know that the expectation must be bigger than like 3, right? So let us assume it is 3.5. And now, using Markov inequality, we know that this probability is less than or equal to the expectation of x over 5. I think here expectation is 3.5. So it is 3.5 over 5 is 0.7. So now again, the upper bound for the probability x is no less than 5, is 0.7. So now let us consider another case. When x follows a completely different distribution, what will the bound change? So if now x, the PDF of x looks like this. And here is 5 again. And here is 0 and then 0.1. This is a PDF. So we know the probability that x is bigger than or equal to 5 will be the error for this shaded region. Because it's the integral of the PDF from 5 to infinity. And we know, obviously, the expectation of x right now is more towards 0.1, right? Because the high density region is around here. So when we do the weighted average, the weighted average must be toward this direction. So the expectation, say, is 0.15. And now, using Markov inequality, what's the bound can we get? Again, it is less than or equal to the expectation of x over 5, right? So here expectation is 0.15 over 5, which is 0.03. So now we get a much smaller bound. So from this example, we can say how the distribution of x affects the bound for the probability. Right? And the properties of distribution is reflected in the expectation term in the bound. Now let us look at some detailed example. Suppose there is a data university, and we denote the amount of coffee the faculty in this university drink in 1 week by C. This is a random variable. And we assume, on average, those faculty drink like 20 liters coffee in 1 week. So now I want to bound the probability that on some week, the coffee consumption is bigger than or equal to 50. How can we bound this probability?
So we know the PDF.
Yeah, direct application. Right? So it is less than or equal to the expectation of the coffee assumption divided by the value, right? Turn 50 here. So that will be 20 over 50, which is 0.4. So basically, from this bound, we know that the chance the faculty drink more than 50 liters of coffee in 1 week is relatively low, right? It's less than 0.4. So this is one direct application of the Markov inequality. So when you are giving some new random variables and expectation, but you must ensure that this random variable is non-negative. And in our case, the liters coffee drink, the amount of coffee people drink must be non-negative, right? So this is a mark of inequality. But what if I want to use mark of inequality to bound probability like this, x minus ex, bigger than some value? Is it doable? This is the original version of the mark of inequality, right? So can we convert it to a bound for this? So actually, it's who said this? Yeah, go on.
Because you can then say that the bound is the expectation of that difference.
Yeah. So we can manipulate this inequality. So we know that x is no less than alpha. This inequality is totally equivalent to what? Subtracting the expectation of x on both sides. These two inequalities are totally the same thing, right? Identical. That means that the probability of this is probability of this. And we can use the same upper bound for this probability. Okay. So it is less than or equal to expectation over alpha. And now we can do some variable substitution. We can redefine this alpha minus ex by some new value epsilon, namely the tolerance level. And now we can express alpha by epsilon plus ex. And now we can replace alpha by epsilon in this inequality. And now we end up with the probability of x minus ex is no less than epsilon. It's less than or equal to expectation over alpha. But here alpha is represented by epsilon plus ex. So now we end up with the concentrated version of Markov inequality. So concentrated version means that the difference between x and its expectation. So now let me write down the Markov inequality, the original Markov inequality and its concentrated version. So if you feel uncomfortable about how to derive this, you can follow this step by yourself after the class. It's very straightforward. So this is about Markov inequality. And next we introduce the Chapter inequality. So Chapter inequality can provide you a tighter bound for this, but it requires more information. So Chapter inequality states that for a random variable x, we know the expectation of x and variance of x. But we no longer restrict x must be non-negative. X could be negative, no problem. And the expectation of x could be negative as well. It's totally fine. And then Chapter inequality says that the probability of the absolute value of difference between x and expectation no less than some level epsilon is less than or equal to the variance of x divided by epsilon squared. So this is a Chapter inequality. We can compare the concentrated version for the Markov inequality and Chapter inequality. Chapter inequality is born as the concentrated version because here is the absolute value of x minus ex. And now we can compare the two bounds. What can we observe? What can we observe? First, we can find that here epsilon is taken to be square, right? But in the Markov inequality, epsilon just epsilon. So what does it mean?
You can do negatives.
What?
You can do negatives.
No. It's not possible. If epsilon is negative, this is something must happen, right?
Well,
Because it's absolute value.
yeah, so you can have negative values inside.
Yeah, you can see that, but it's not some key point. You can consider when we increase epsilon, then how the change of this upper bound from Chebyshev inequality. Yeah, I heard someone saying that. Decrease quadratically. Means it decrease very fast. But if you increase epsilon here, what happens? Of course, this bound also decreases, right? But decreases linearly. So we can say how the bound is tightened when we increase the epsilon. So obviously, Chebyshev inequality can provide a tighter bound.
But the catch is you need to know the variance. Is that the catch?
Yeah. There's no free lunch, right? If you want to get a tighter bound, you need to know more information about x. So now let us look back to our coffee drinking problem. So again, in the data university, we denote C as the per week coffee assumption. This is a random variable. And as in the previous case, we assume the expectation of coffee assumption per week is 20 liters. And suppose further we know the variance of the coffee assumption, which is 9 square liters. Namely, the standard deviation is 3 liters. And now let us compare the bound we can get. We want to bound the probability that on some week, the faculty consumes more than 50 liters coffee. Right? So using Markov inequality, which is straightforward, right? We just calculate it. I do not repeat it again. So it is less than expectation of C over 50, which is 0.4. Now let us consider how can we use Chebyshev inequality to obtain a bound for this probability. How can we do that? To apply the Chebyshev inequality, we first need to get a form that the random variable subtracting its expectation, right? How can we get here?
Subtract expected value from both sides.
Yeah, that's the same trick we just used, right? So we know C is bigger than 50 is totally equivalent to C minus expectation of C bigger than 50 minus expectation of C. These two inequalities are totally equivalent. And what is the expectation of C? 20, right? So I can simply replace the right hand side by 50 minus 20, which is 30. So now the problem ends up to be how to bound the probability C minus expectation of C is bigger than 30. It looks like still not applicable to the Chebyshev inequality because Chebyshev inequality says it is the absolute value between their difference bigger than some level, right? So now let us try to first blindly apply the Chebyshev inequality. So what can we get? we know that according to chapter inequality, the absolute value between C minus EC bigger than 30 is what? Is less than what? Using this upper bound, right? It's less than or equal to the variance of C divided by, here, epsilon is 30. Right? So it is 30 squared, because when it's bigger than epsilon, so in the upper bound, the denominator will be epsilon squared. So we directly apply the chapter inequality, and here we end up with the variance of the C is 9 square liters, right? And the denominator is 30 squared, which is 900. So the bound is 0.01. Then what kind of connection between the probability that C minus EC is bigger than 30 and the probability that the absolute value of C minus EC is bigger than 30? What kind of connection can we get?
Sorry, what was that question?
So can we make the connection about this probability and this probability?
You can split the absolute value.
What?
Split the absolute value. So you can have minus 30 is greater than C minus expected
Right.
value of C.
Right. So we can look into this equality, right? So what does C minus expectation of C bigger than 30 mean? It means either C minus EC is bigger than 30 or C minus EC less than minus 30, right? They are equivalent. So actually, this inequality indicates two random events. The first event is C minus EC is bigger than 30. And second event is C minus event is less than minus 30. So denote this event by A and denote this event by B. So actually, this is to say either A happens or B happens. So the probability of the absolute value bigger than 30, it is the probability of A happens or B happens. Right? And now let us look at this probability we are interested in. What's this represent for? This actually represent this event, right? C minus EC is bigger than 30, right? C minus EC is bigger than 30. So actually this probability is just the probability that even A happens. So now, what can we conclude about the probability of A happens and probability of A or B happens?
It's twice the other.
One's twice the other. Can we compare their values? This is something we have reviewed in our first or second lecture, right? So we know that probability of A must be smaller and less than probability A or B. This is very obvious. So A or B is usually represented by union. So now what can we obtain right now? Probability of A is probability of C minus EC is bigger than 30, right? Here. C minus EC is bigger than 30. Less than or equal to, what is the probability of A or B? 0.01. 0.01. Yeah, later we can actually. Here, right? This is A or B, right? Right? And now from Chebyshev bound, what can we get? We know this probability is less than or equal to 0.01. Means that we just copied it, right? So we know this bound is less than. So finally, we end up a bound for this probability. And as we just mentioned, this is equivalent to say the probability of the consumption is over 30 meters. So now we use a Chebyshev inequality to obtain an upper bound for the probability we consume over 50 liters, which is 0.01. But using Markov inequality, what kind of bound we get? 0.4. So which one is better? Yeah, Chebyshev. Why is better? Yeah, we have tighter bound. Why we can end up with tighter bound? Because we know extra information about X, the variance of X. So can we obtain an even better bound? So let me write down the Chebyshev bound here. So we know the probability of Chebyshev bound. What is x minus ex is absolute value bigger than or equal to epsilon, less than or equal to the variance of x over epsilon squared. The k is in the square. So now let us look at the sample mean stuff again, right? Suppose I have a IID sample, like n IID sample, and I take average over the n random variables. And we know the expectation of x is the true mean for some underlying distribution. Okay? And we know the variance of x is 1 over n of the variance for the hidden distribution f that each ID data sample or random variable follows. So now, can we use Chebyshev inequality to bound the probability that the sample mean deviates the true mean by epsilon? Straightforward, right? Pretty straightforward. So we can bound that the probability difference between the sample mean and the true mean, less than epsilon, is smaller than the variance of the sample mean. So what is variance of sample mean? Here. Let us just copy here. That's 1 over n variance of the hidden distribution f divided by epsilon squared. So now we can move n from the denominator to the from the numerator to the denominator. We end up with the bound for this error level, as we mentioned in the beginning of our lecture. So then there comes a very interesting question. Suppose I want to get a sample mean such that first I'm designated epsilon and delta. I want to guarantee this probability of the error bigger than this epsilon, always less than the designated delta. Then how many samples, how many data points should I at least use?
Depends on your epsilon and delta.
Yeah, of course, it depends on epsilon delta. And right now, we assume epsilon delta is designated, is known. Say, epsilon could be a 0.01, delta could be a 0.005. So now I want to choose a certain number of data points such that we can guarantee the chance that your sample mean deviates from the true mean by 0.01 is always less than 0.005. Then what is the number of data points I should use to calculate the sample mean? Can we obtain such a sample number? So this problem is called sample complexity. Meaning that to achieve some particular performance, how many data points should I use?
So we set the variance over n epsilon equal to delta and solve for n.
Isn't this?
Yeah.
Yeah, you're right. To obtain a reasonable number of samples, to make this guarantee always hold, what can we do? We can make this upper bound always less than or equal to delta, right? So if we can solve the number of samples n such that this upper bound less than or equal to delta, and then this probability must be less than or equal to delta. So now this sample complexity problem is reduced to solve this inequality. And turns out to be n is no less than variance for the hidden distribution f divided by epsilon squared and delta. So now you can replace epsilon by 0.01 and delta by 0.001. And of course, if you know the variance for the hidden distribution, you know the exact minimum number of data points you need. So this is kind of a reverse problem, sample complexity problem. But it can also be solved using this bound. Okay, the last inequality we need to know is called Chernoff-Hopf inequality. So Chernoff-Hopf inequality usually ends up with an even tighter bound for this. But of course, there's no free lunch. We have to know more information about the random variable. So here is the Chernoff inequality. So it says, okay, we have a set of n random variables which are IID. We're interested, we know the expectation of each random variable. Actually, they are all the same because they are IID. And also, we know the range for each random variable. Say, we know the range for each random variable, it is between, say, B and T. And then we can denote the length of the range by delta, T minus B. Then we are interested in the sample mean. That is the average of these n random variables. So this is a condition for the usage of Chernoff. And given this setting, we can claim that the probability of the sample mean, the distance between the sample mean and the true mean, that is expectation of any random variable, bigger than epsilon, less than or equal to this new bound, 2 minus exponential minus 2 epsilon squared n and over square of the range, square of the length of the range. This is third bound. So all we need to know is that the range of each random variable. So now we can compare this bound and the bound derived by Chapter inequality. So these two inequalities all regarding the error of using sample mean to estimate the true mean. Remember, true mean here is the mean for each IID random variable. So what can we observe by comparing the two bounds? Which one is better? This bound and this bound. Which one is better?
The share of inequality. That one's better.
Why?
Because it will grow, or the bound will be decreased much faster.
Yeah. Why?
Because the exponent
Yes.
raised
Yes,
to-
exactly right.
It's a negative exponent.
So we know that when we increase the number of data points, our estimation for the true mean will be more accurate, right? But from Chebyshev inequality, the bound is proportional to the number of data points, right? But now from the Chernow-Hopkins inequality, the bound is exponentially decaying with the number of the samples. So when you increase the number of data points, you get a you will see a much smaller upper bound for this probability.
So the main difference is that we just know the range.
Yeah, we just know the range.
Okay.
You even do not know. You do not even know the variance. There's no variance here. You just know the range for each random variable. So of course, if I want to solve the sample complexity problem with the Chernow-Hopkins bound, what can we do? If I want to designate a epsilon and the tolerance level and the probability of failure level, I want to find appropriate number of samples to ensure the error, the chance of the error bigger than epsilon must be less than or equal to delta. How can we do that? Using Chernow's bound. We can do the same thing, right? We can solve the number of data points we needed to make this upper bound further less than or equal to the designated bound. And then we solve this inequality, we can ensure this probability must be less than or equal to delta. You can solve it. It's let me just copy the result here. So it's sigma delta square 2 sigma square and logarithm of 2 over delta. So this is sample complexity derived from Chernow bound. So we can say, actually, when we decrease delta, we require more and more accuracy. The number of samples actually increases log speed, right? But if we compare with the Chernow bound, which is sigma squared over epsilon squared and delta. If you decrease delta, meaning that you want more accuracy, and then the number of data points you need grows linearly. So now you can see the advantage of the Chernow bound. Because using Chernow bound, actually the real number of data points you need is much less. From practice, it means that the more training sample you have, the more computational resources you need to use. If you have a limited number of samples, you can save the computational resources.
So which one of these inequalities are most used then?
Most used is Chernow bound in the theoretical paper. But sometimes it will involve the Chebyshev inequality. Okay, I guess we should stop here. And next class we will give some example by using the Chebyshev and Chernow bound to derive the concentration bound for different applications. And hopefully that you will know how to apply this bound.
if